I've entitled this discussion Enterprise Application Data and In-Memory Databases. And as I was mentioning a moment ago, and as I've talked about in some of our previous discussions, one of the things we will be talking about in this discussion is SAP HANA. But realize that SAP HANA is one example of an in-memory database, and there are other competitors of SAP that have their variations on these systems as well. So some of the things we will be talking about will perhaps be SAP specific, and when we get to those elements, I will mention that. But otherwise, a lot of the things that we will be talking about are reflective of contemporary database and enterprise application systems that are marketed by many organizations. So I think this should be a very interesting discussion for us as we go through this. Please do make sure that you stop me with questions, many different things that we could talk about, and so I'm happy to take those on as they come up here. So one of the challenges that we face in a contemporary organization is there are lots of different types of data that we might find ourselves having to handle within an organization. So this slide, you'll notice right here in the center, it talks about challenges related to data management. So this is not necessarily an exhaustive way of dividing these things up, or the only way that these things can be divided up, but you'll notice that there are at least 4 different kinds of data that we might see in our organization. Let me see if I can get rid of this dialog box here. A lot of what you have worked with this semester and a lot of what we have talked about falls into this upper left quadrant here of transactional data. Transactional data comes to us, of course, from machines, from computers. It comes to us from transactional applications or even apps that might be run by an end user or an employee. This kind of data entry, this kind of data comes from interaction with a user. Can anybody give me an example of what would be transactional data that we might find ourselves having to handle on an ongoing basis in an organization? What would one example of that be? Okay, well, I mean, that's from a technical perspective, but just looking at the data itself, what kinds of data? Sales data. Yeah, we're a company and we sell things, and so on an ongoing basis we're collecting sales data from customers. That would be information about our products, information about our customers, addresses, prices, all kinds of things that once again you've dealt with in some of your lab activities. Those are transactional data elements. And as was mentioned just a moment ago here, we've talked about OLTP systems, online transaction processing, and right in that term, OLTP, is the word transaction. So a lot of what we do in organizations is transactional data entry and then transactional data processing. And so that's a kind of data handling that has been with us for quite a while. Well, if we move over to the upper right quadrant, you'll notice now we're looking at this idea of analytics, and in particular doing analytics on structured data. And this is something that you have gained some experience with this semester as you have used a tool like Lumira, or even Excel would fall into this category. And you notice that what we are doing here is reporting. We're doing what we would call classical analytics. We're doing planning. We're doing simulation. Simulation here in this context would mean things like what if? What if this happens? What would we do? What would the result of that be? And so this is another fairly traditional kind of information handling that we see in organizations. And this would be characteristic of what we have talked about before as well, OLAP, online analytic processing. And so the top part of this diagram are things that we have talked about. There are things that are fairly traditional in organizations. These are not in any way new. They're challenges that have been around and opportunities that have been around now for really a couple of decades. But as we move to the bottom of the diagram, we're now starting to see some things that are a little bit on the newer side of things. On the left here, we have event processing and stream data. Now notice the sources for this. This is machines once again, but also sensors, high volume systems, and things of that sort. So the idea here is, as opposed to this being data that's being manually put in by people, and someone sitting behind a computer and typing something in, which would fall into the category probably of transactional data, what we're talking about here is some kind of automated system that is generating a stream of ongoing data that just keeps coming at us with data. What would be an example that you perhaps are familiar with or could envision of stream data that an organization might have? In what respect?
Like live feed, like live stream.
Yeah, I get that. YouTube would be, I don't know that we'd put YouTube in that square, but I don't know where we would put YouTube. It kind of depends on whether you're YouTube or you're looking at it from the user's perspective.
It was represented as unstructured data, so it might go.
Yeah, I'm thinking that. Now you were saying something. What?
As in for at Uber, the location of your car at any time.
Okay. All right. Excellent. So like an app that is continually reporting my location by way of sending GPS coordinates to some third party would be an example of stream data. Other examples of stream data that are pretty common would be if we go down sensors here. You might have, let's say, temperature sensors. You might, on a piece of equipment, might have something like product counters. One of the areas of interest right now is something called the smart grid. I don't know if any of you have heard of that, but the smart grid, one facet of that is electricity. And people now can have smart thermostats and smart electric meters put into their home that monitor your electric usage on an ongoing basis. Well, the idea behind this stream data is, and whichever one of those examples you want to think of are all examples of the data is being generated just on a continuous basis. Imagine, for an example, if I was running an app here, maybe I'm an Uber driver. And as I drive my Uber vehicle around, the app keeps track of my location because it puts it on a map where other people using Uber can see it. Well, that means my phone is almost continuously sending my GPS coordinates up to the cloud, and something is grabbing those GPS coordinates, consolidating it with other Uber drivers, and sending it back to other people in their devices. So as you think about stream data, let's think about that for a moment. What would you see as a challenge related to stream data that might be unique to it as compared to the other two types of data we've talked about? How's it different, and what kind of problems does that create? Really big and really fast. I mean, if you think about this, somebody driving a car at 45 miles an hour, how often do you need to know their location in order to update your map? You know, maybe you'd want to just figure out their location every, let's say, 3 or 4 seconds. Well, if you have thousands of drivers driving all across the US and you're trying to track their location on a per, let's say, 5-second interval, think about how much data that is. Think about like a thermostat on the wall, and I don't know how smart the one is here that we have on the wall of this conference room, but you can see quite clearly if we open that up, there's a networking jack in there that's hooked into a computer system. So somewhere on campus, somebody could pull up a display and find out information about this room. That sensor is continuously generating information. So what are we going to do with that information? You know, if you think about it, at a big company, transactional data entry, you know, at a really, really big company like Walmart, you could be looking at gigabytes of data a day. You could hypothetically even be looking at terabytes of data a day, probably nothing bigger than that. Well, if we had a factory and all throughout that factory were sensors, just keeping track of the temperature, how much data might those sensors generate on a daily basis that's being sent back to the system? It's a lot of data. So immediately that points to one area of difference between transactional data and stream data. And so I'm going to ask you a really hard question here and see if you can figure this out based on our conversation. What is one of the critical pieces of OLTP systems that is critical that we not do with stream data? So let me hit you with that again. It's almost like a IT riddle. What is something that is critically important that we do for transactional data that we can't do for stream data, or we'll find ourselves in trouble real quick?
Doesn't it process small amounts of data for transactions?
Okay, so we definitely have a difference here as far as data size. I'll buy that. Okay, what other differences are there though?
Objectives and opposites.
Okay, okay. What's that? Cleanup data, is that what you said? All right, that's a good point here too. What, and we've got a lot of things that are on the right track, but no one said the exact magic words. What is it critical that a transactional data system not do? What's that?
Downtime.
Why is downtime bad? And, okay, keep going. Why is downtime bad? Because what happens during downtime? I know you guys know this. I'm trying to get you to come up with it though.
Okay, we don't have the data for that period of time. We can use data with transaction. I mean, without the transaction, we cannot afford to miss getting some data. But with that process, you can afford to lose some data.
Okay, so we finally hit on it. Very good. Transactional data systems, and I've given you a metaphor before that we'll probably refer to. Transactional data system is like a giant vacuum. The role of this system is to capture this data and we can't lose it. I mean, you would not want to set up a system to capture customers' information on sales and at the end of the day found out that it lost all the sales data from between 1 and 3 p.m. That's no good. Transactional data system has to capture everything. Well, guess what? With a stream processing system, if we capture and store everything, we're going to run out of storage really, really, really quick. Because everything that we have hooked up that's giving us this stream data is like really, really talkative. You know, that thermostat on the wall might report the temperature every second. Do you really want to waste your time storing the temperature in this room every second today? And imagine if every room on this campus had a thermostat like that. Would you really want to tie up all of the storage necessary to store the temperature in every room on this campus every second throughout the day. That'd be a waste of time, right? So how would you imagine that companies tend to handle stream data? What would you do? Stick with that example. Let's assume that you were in charge of heating and air conditioning on this campus, and you knew that every room on this campus had a sensor like that in there. And you knew that it would be stupid to try and store all of the data as it came in. What, though, might you want to do with the data that would be useful?
Well, it sounds like it'd be like using a UDP connection, which can afford, like just like with playing videos online, you can skip frames and it's not going to break anything.
Okay, so we might agree that it's not going to be the end of the world if we miss a piece of data. You know, if this thing's sending data back every second, think about that for a minute. Do you really think the temperature in this room changes radically from 1 second to the next? I mean, over the course of the day, the temperature might change, but from 1 second to the next, the temperature's probably going to be the same. So even though that sensor is giving me data every second, I think we'd all agree that doesn't mean that I need to kind of listen to it every second, right? I can kind of ignore it if I need to. And if occasionally I drop some of the information, it's not the end of the world. What else, though, might be of interest to me with this stream of data?
Possibly you have like a reference data that even though you miss those data, you can always compare your current data to the thermostat to get that baseline temperature. You compare the current temperature.
Okay.
You don't have to go back for look for those missing data to know if you're still in line track. You have to use from the current data compared to your baseline data and see if you're track.
Okay, so let's explore that for a moment. Why might I want to compare my current data to an expected baseline? What kind of things might I be looking for?
Threshold.
What's that?
The threshold that don't go above this point, below this point. Only alerting is above this point or don't alert.
Okay, so I might want to say, you know, I'm going to listen to every thermostat on this campus, but it's not like I'm going to listen to it every second of every day, every minute. But I am going to pay attention to the data I'm getting, and if the data is what I expect it to be, let's say it reports that the temperature in this room is 70 degrees, I might just basically throw that data away because it indicates something's normal. But suppose it's telling me that the temperature in a room is 95 degrees. Well, that might be of interest. You know, that could indicate that there's a fire, or it could indicate that just something weird is going wrong because 95 would be really, really hot. Similarly, if the thermostat told me that it was 50 degrees in a room, that might be something weird too. So a lot of times what we do with stream data is we don't make any effort to store it and archive it, but a lot of times what we do is we monitor it to look for anomalies. We look for things that are out of range or unexpected in some way. And depending upon what the data stream is, would tell us what that is. It could be temperature, it could be, you know, if we have what a lot of times will happen with the smart grid with electricity. I don't know if any of you have experienced this. I don't know if any of you are homeowners, but being a homeowner, I can remember that it used to be that if your power ever went out, you were supposed to call the electric company and tell them, hey, my power's out. Most electric companies anymore will tell you you don't need to do that because they know when your power's out. How do they know when your power's out? Because they know they're not sending you any electricity. They have meters in your home that all of a sudden now are reporting you're not consuming any electricity. Well, that would be really, really weird because even if you turn everything off in your home, you have refrigerators and other things that are still running a little bit. So if they ever see like a whole block where no one's consuming any electricity, they have reason to believe that something's gone wrong and they'll automatically investigate. So we look for those kinds of anomalies. Let me give you another example. Well, let's forge ahead for the sake of time here. But we have this stream data, and the big point that I really wanted to make is one way that this is different is with transactional data, we play vacuum, and we want to make sure that we don't lose any of this information. With stream data, if we had that philosophy, we'd have a real problem, because we could be looking at having to store an awful lot of information that may have no utility to us whatever. And I will tell you that in a lot of industries, this is kind of an open question. You know, I've been in meetings where people have said, we have these sensors, they're sending us this information. What would be some things we could do with it? And some people have said, well, we could do this with it, we could do this with it, and many times they've been able to come up with good applications, but a lot of times they don't know what to do with it, so they don't do anything with it at this point, with the idea that maybe at some point in the future they'll be able to use it. Well, we've got one more quadrant here, and this is unstructured data. Now, sensor data, like the other kinds of data that we have talked about, tends to be structured. You know, maybe this thermostat every second creates a packet that's in a particular format that has the temperature and maybe even some other statistics. It might report the current temperature and what the thermostat is set at every moment, and it comes in a packet, and we know the format of that packet. The data is very structured. Well, there's a lot of data now that comes into organizations that is very, very unstructured. The web is a fabulous source of unstructured data that could have tremendous value. Can anybody think of one website in particular that is widely regarded to have a lot of potentially useful information, but the data is extremely unstructured? I'll give you a hint. It's a website probably many, if not most, if not all of you visit every day.
Google, Facebook.
Google would be an example, but Facebook's what I'm thinking about. You know, do you realize, imagine if a moment your brain knew and understood everything on Facebook. Do you know how many things you would understand? First of all, you'd probably have like the recipe for every kind of food in the world that anyone's ever eaten. And you'd have an endless supply of cute cat and dog videos and things like that. But you'd also know things about what people think about politically, what people think about as far as favorite sports teams, who's popular, who's not popular. I mean, if you really could process all of that information and understand it, you realize all of the things that you could glean from that.
Be the world's best marketer.
You could be the world's best marketer. But there's a problem with all that data. It's very, very unstructured. And unstructured data is really, really challenging. And a great example of this would just be people's Facebook updates. A Facebook status update could be, 5 characters, or it could be a paragraph. And as you look at, on any given day, how many status updates and posts there are, and it's all just free-form text. And in fact, it's all free-form text in probably every language spoken on this planet. And the idea is, how could we process data of that sort? Because it is very, very hard for a computer in particular to understand that information. So that takes us in this dimension of text analytics, which is where we try to develop algorithms and techniques that a computer could use to understand people's sentiments and to understand what people are thinking, or just to gather information from unstructured data. Part of what makes this really challenging is you have people that post something like, I like and I'll just not write this out, I like getting punched in the face. Well, if you saw where somebody wrote that as their Facebook status update, first of all, you would probably think either that person is really weird or they're being sarcastic. They don't really mean they like getting punched in the face. They were being sarcastic and say, oh yeah, I like getting punched in the face. Well, the thing is, computers are horrible at understanding sarcasm. They don't really understand jokes. They don't understand humor. And so when you turn a computer loose on unstructured data, unless you have a very, very good algorithm guiding it, it's very, very challenging for that information to be processed in a way that yields understanding. Well, we not only have things that come to us from sources like Facebook, we have other social media. Twitter's a great example of that generates a large amount of potentially very useful information during political campaigns. Most political campaigns use extensive analytics tools to try and understand what people are tweeting about and what they like and they don't like. But even beyond social media, we have log files. I had opportunity to, over the summer, I took an advanced security boot camp course. And one of the things that was talked about was log file analysis. And one of the things that was mentioned is an organization might have a router that is hooked up to the internet and is part of their infrastructure for serving up web pages. And that router and other equipment keeps log files of all the different activity throughout the day. Well, now we're looking at data that looks a lot like this stream data because it's a very, very large data set that gets generated. Well, the thing is, if you looked at that router file and really, really analyzed it, you might be able to discover some kind of security flaw that you have in your organization that someone has been able to exploit. But the challenge is you'd have to pour through a log file that might be hundreds of thousands of lines long looking for a sign of something awry. Very, very challenging. How do we do that? As humans, we can't do that. But what we can hope to do is create computer programs that will scan through that data and help us find things that are anomalies that we might want to look at more carefully. So the whole point of this slide is there are all kinds of different data that we might have to deal with as an organization, and we have to come up with strategies and techniques for how to manage this data. Now, this is a very contemporary problem. Some of these things have been with us for a long, long time, but event processing, stream data, text analytics, unstructured data, this is the challenge of the decade that we're in right now, and no one has come up with the definitive solution to this. These are things that companies are wrestling with now to try and figure it out. We don't have to go back very far to we're in this era right here. I'm kind of curious, how many of you even know what this is right here in the upper left corner? Anybody know what that's called?
It's been a long time ago.
Dot matrix.
It's what a dot matrix printer used to use, but I'm just amazed because if I would go back, I wouldn't have to go back that far. If we went back 10 years and I asked that question in this class, every student would know what that was because it was so commonplace, and now nobody even knows what this is. This is what I was going to say used to be called. I guess it's still called this, although you don't see it as much anymore. That's green bar paper. And it was just paper that had these little tractors on the side for feeding through a dot matrix printer, and it had the green and white striping on it that made it easier, at least ostensibly, for you to read what was on it. And the reason why I say 10 years ago everybody would have known what that was, that's how when you printed out your source code from your programs, you would get it on green bar and look through it and figure it out. And so that's not that long ago that green bar was very, very common. Some of the other things here are a little bit older. You probably all know what these are, right? What are these things right here? Those are punch cards. I'm sure none of you have ever used a punch card, have you? You know, it was not that long ago, although admittedly this is now even old for me, where the idea was this is very common for this to be a transaction. So if you were to call up, let's say, J.C. Penney on the phone and place a catalog order, the way they would feed your order into the system would be typing it onto these punch cards. And there were machines that were probably about the size, you'd say, of a refrigerator turned on its side, that would have a stack of these cards in it and a typewriter keyboard, and you'd push a button to have it load up a punch card, and then you'd type, and if you made a mistake, no way to fix it, you have to throw that card away and start over. But you had 80 columns that you could type on, and you could code up a transaction. And when you were programming, every line of code used to be one punch card. So if you had what would now be a 200 line program, you'd have a deck of 200 cards, and you better hope you never dropped it, because good luck ever putting them back in order. But that used to be a thing. Students would, and this is before my era of teaching, although I have used a punch card machine. But Dr. Bales, all of you know Dr. Bales, when he first started teaching, punch cards was the way it was. And you'd code your program on punch cards, and then you'd run them through a machine. When that got more sophisticated, you had this guy over here on the right. This is punch tape. So it's the same kind of idea, but it's now on a continuous spool of paper tape. You actually still see that in some really, really old school systems, like anybody familiar with what I'm talking about when I say a player piano, a piano that plays itself? A lot of times they run on things like that with paper tape. This guy right here on the bottom left, he's one of my favorites. I don't know who invented this on the left. This is what was called a crush pack tape deck. And this is when they invented magnetic storage, but had not yet invented what you see here on the right, which was the spools that you could put stuff on. So this was on the left and the right. You literally just had like these big buckets that had magnetic tape in it, and the magnetic tape would run through the machine here, and it would just get dumped in a big old mess on the left and the right as it fed through. I mean, what's that?
That's our database.
Yeah, that's your database. It's a little bit more organized than that, but I can't imagine how often that tape would snap and other things there. This guy right here, this is like one of the really, really popular old computer systems. This is an IBM 360. This was what computers looked like in the 1970s, and everything about that picture right there kind of looks like the 70s to me, with the red and the blue and the way people are dressed and everything. The very first computer that ETSU ever bought as a university was the IBM 360. And the Department of Computing is, I think this is our 42nd or 43rd year of operation. So that's what the first generation of computing students used. And there are actually some of those people that are still on our advisory board and affiliated with the department. And they used to talk about during the day, the university used the computer to run the university. And at night, that's when all the computer classes were. And that's when the students got to use the computer. And so they said, it wasn't unusual to be, standing outside. They really got to know each other because they'd have class every night, kind of like you experience as grad students. And that's when they would, write their computers and everything, or their programs, everything else. And it was using the IBM 360. Well, what was characteristic of the way data was processed in regards to everything that we're seeing up there was everything was handled as a batch process, which meant that let's say we were J.C. Penney and we took in orders from customers. All of those orders throughout the day would be punched onto punch cards or in some other way coded into some intermediate format, and then at the end of the day all of those cards would be run through the system in one batch. And so what you would have is kind of these waves of data going into a system. And so you would feed in a whole bunch of punch cards, and then you would get back probably printouts on green bar that would show you your sales transactions for the day and orders that needed to be shipped out and things of that sort. Now, if we really think about what this represents, this is a lot better than when everything was just done on paper. Because paper, it's hard to aggregate information, it's hard to sort information. I don't think we need to go down a great discussion of why paper is bad and why this is better. But one of the challenges that you have with this is by the time you saw anything on green bar, chances are pretty good that the information was already out of date. You know, there was no such thing as like live information. Notice nowhere on this slide do you see anybody working with a computer monitor. The closest you have is this guy right here, and this guy right here is using a technology that is, I guarantee you, none of you have ever used before. It was the most, if you like to conserve paper, it was like the most horrible thing ever invented by mankind, probably. That was a hard copy terminal. Imagine interacting with a computer by way of a typewriter, if any of you can even remember a typewriter before, where you would type something and then it would show up on paper. Okay, so imagine you log into the computer and you say, show me all the files in a directory, and it prints it out on a piece of paper. And then you look at that and you enter the change directory command, and you type that on paper, and then it prints out. I mean, it's like, instead of on a screen, everything. And when you were done, I've used those for, it's kind of like, if any of you use terminal programs now with logging, and you're familiar with how you can scroll back through and see your history, this was the old school version of that. Because you didn't have to scroll through anything. You could just flip back through the pages of paper and see what you did 10 and 15 and 20 minutes ago. That was a hard copy terminal. That's what you had before there were even monitors like we have today. So we don't have to go back very far to find where this was the way information was handled in organizations. That's batch data processing. Well, what happened after that? Now we move to what we have now, which, if you've seen this, and we talked about OLTP, and we said that stood for online transaction processing. Anymore when we hear the word online, we tend to think about the internet. But what online meant in the early days was just, this is not batch. This is not where we're going to accumulate everything and put it in these big batches. Now we're going to put in the information as it occurs, and we can look at information being updated in close to real time. And so we have something here on the left that looks very familiar to you guys. This is a screenshot from the SAP GUI. This would be an example of online processing. You put information into a system, you can actually see it on a screen. Other users in your organization can see it in real time. And of course, now we have more contemporary applications, like what you've been doing in your lab work, where we can create visualizations, we can create charts, we can do all kinds of things using this data to make it even easier for people to understand what's going on. Well, as we've talked about, even with this online processing, the challenge that a lot of organizations have had is it requires a lot of computing resources to accomplish this kind of online processing. So much so that we really cannot devote computing cycles and computing processor power to doing anything very sophisticated in the form of analytics. So we use this ETL process to move data out of our online systems into what we call this thing that's here on the right side of this diagram. What have we called it before? No, not a dashboard. I'm talking about the thing here at the bottom that looks like a... Yeah, that's a data warehouse, okay? So the idea here is we're moving information out of our transaction processing systems. We're extracting it, maybe doing some transformation. We're loading it into a data warehouse that then we can do analytics on. Now the question is there a big difference between batch processing back here and online processing here? And the answer is absolutely. There's just a huge amount of difference in the way we work in our organization and the things we can do. But the next question then is, well, what's the next step? Where do we go from here? And that's what contemporary organizations are taking their next step with. Because there are some challenges with online processing in most organizations, and a lot of it revolves around this right here, which is, we said a moment ago that by the time you saw something on green bar paper, it was probably out of date. Well, anymore, by the time you see something in a data warehouse, it's probably out of date. Now, it may not be as out of date as it would have been if you were looking at a hard copy, but the fact is, it's not real-time information if it's loaded into a data warehouse, almost by definition. So I'm going to skip over this slide because we have talked about OLTP versus OLAP already. So what's our contemporary goal? Our contemporary goal in a lot of organizations is, we have ETL, but we would like to get rid of this. We would like to be in a situation eventually where we no longer have OLTP and OLAP, and you have to apologize, I don't know why I get these little horizontal lines every once in a while. If anybody has a Microsoft Surface and knows why those show up, I would love for you to tell me, because I just get these weird little crossbars every once in a while like that. I don't know what causes that to happen. But so the idea is, what we want to do is figure out a way to bring these together so that we can do our analytics and our transaction processing on the same system. Because that will lead us to what our big goal is here, and we've talked about this before. We want one source of truth. A lot of what we focus on in data processing and IT is helping people understand what's going on. And we want to know what the true situation is. The true situation may be good, the true situation may be bad, but the only way we can react in a meaningful way is if we know what's really going on. And if I give you a bad set of facts and ask you what you should do, and you tell me what you're going to do or what you should do, and then you do it, if I gave you a bad set of facts to begin with, it's very unlikely that whatever you do is really going to be helpful. So what organizations really want to make sure is, as they look at how they handle data in their organization, they want to have it so they get true insight into what's happening in their organization, and they have one source of truth. Now, why is it challenging to say, let's get rid of this dividing line between OLTP and OLAP, and let's just use one master system for everything? Why is that challenging?
I know in technical terms, I believe some studying some papers on this is possibly you're trying to make a hybrid structured and unstructured database.
So we have we talked about this a few slides ago. We have structured data, we have unstructured data. How are we going to process them? How are we going to process them together? And how are we going to process them in some kind of efficient manner? That's going to push the capabilities of contemporary computer systems. See, a lot of what our problem focuses on when you get right down to it is computer power. You know, we tend to think of computers as being very, very powerful devices, and they are, particularly as we compare them to what we looked at a few moments ago, which is what these systems looked like a couple of decades ago. But the fact is, if I told you, okay, as a homework assignment, write a database to capture all of the information on Facebook, and then write a program to go out there and grab all that data and put it in your database, okay? And let's assume that all of you, being brilliant, could design such a database. How much information would that be, do you think, to capture all of that? And how much more information coming in every second? I mean, and how powerful a computer would you need? You know, how many computers must Apple, must Google, must Facebook have? You know, they don't have just like one machine. They have thousands and thousands of machines all hooked together, and Facebook's only concerned about Facebook, and Google's only concerned about Google. Well, in contemporary organizations where we're trying to solve these problems, we might not have as much data as they have, but we still do have the challenges of structured versus unstructured data. We have challenges related to computer power, and so we've got to figure out how to handle this information in a way that would give us one source of truth that would let us do, ideally, what we would like to do is understand the reality of now. You know, what's going on right this second in our organization? What is it that in the last half hour people have bought in our stores? What is it in the last half hour that we've been making in our factories? And do we have any production problems in any of our factories? And what are those problems that we're having? We want to understand the reality of what's going on now in our organization. Well, as we look at enterprise data, where is most enterprise data stored? This is not intended to be a trick question. It's intended to be pretty obvious. And it's actually been mentioned in the last 5 minutes. Where do we store enterprise data? What's that? In a data warehouse, or more generically even than a data warehouse. A relational database. And a relational database is made up of what? Tables, okay? So we have database tables, okay? We have an abundance of database tables. I might have told you this before, but an SAP ERP installation, and some of this is changing, but historically it would not have been uncommon for there to be over 125,000 data tables, okay? That's a pretty complicated data model. Well, let's talk about these database tables. There's what you guys have learned in your database classes about data normalization, and then there's what tends to happen in real-world enterprise databases. And sometimes those things are not at all the same, okay? It is not at all unusual to see in some SAP database tables for there to be 160 plus fields in one table, okay? That is not at all unusual to see data tables that are, I'll characterize that as very wide, okay? So enterprise data, I'm just going to abbreviate this, enterprise data tends to be wide, which means that, you know, in your database class, you might have created database tables with 5 fields and 10 fields and 15 fields. But when you get out into real enterprise databases, you tend to see a lot of database tables that have a lot of fields in them. And SAP has even done some things that are crazy, that in their database fields, that and other vendors have done this too, where you get to a point where the table is so wide, you actually take one field in your database table and you make it 10 different things. And you like pack 10 different things into one database field, just for the sake of you're running out of field space, okay? So enterprise data tends to be very, very wide. But here's the thing about this too. Many columns tend to be empty. It is not at all unusual to see a database table that has 160 fields, and then if you go and look at the contents of the table, 50 plus of those fields have absolutely nothing in them at all. They are maybe a data point that our company doesn't even need to keep track of. And so we have a database table that has 160 fields, of which 50 of them are totally empty. So what you will see is this characteristic. These database tables are sometimes described as sparse and wide. Okay, so you have a lot of fields, but you have a lot of empty space. And then we also see this. So we've talked about columns tend to be empty. Many rows tend to be redundant. Give an example of what I'm talking about. We have in our company, hypothetical here, one factory. Our factory's in Texas. We ship all of our orders from that one factory. Well, in our database, we have a table that keeps track of when we shipped out orders and from where. And in that database table, every order that goes out shows that it's shipped from Texas. Every one of them. So we have this database table that might hypothetically have millions of rows, but for one field, every one of those rows says Texas over and over and over again. Or you'll have a field that has different things in it. Not every row is the same, but it's a set of things, and it's a fairly small set of things that are redundant. Can anybody give me an example of something you might see in a database table where you might have a lot of rows, but only 2 or 3 variations in one of the fields? I'll give you a really good example. Stuff like this. Mr., Miss, Mrs., titles. If we had a customer database and we stored customer titles, you'd see a huge recurrence of Mr., Ms., and Mrs., maybe with the occasional doctor or coach or something like that. But you would tend to see a lot of redundancy there. You would see fairly obvious redundancy if we were storing information about people and we had, for example, a gender field, okay? You wouldn't see a lot of different things being stored there in that field, even though you might have a huge number of people. So what we tend to see in database tables is we see very, very wide tables, but a lot of very, very empty cells. And in fact, SAP a number of years ago commissioned a study where they got a fairly robust set of their customers just to let them go through and explore their database. And they discovered that 55% of columns were unused in database tables. So, basically what that's saying is more columns are basically a part of the database design, but don't have any information in them than ones that are part of the database design and populated with data. So enterprise data has some really interesting characteristics to it. So the question becomes, as we continue to explore this, how can we use this to our advantage to try and solve some of the problems that we're facing? And so let's make the transition here, and let's start talking about this idea of in-memory column store databases. We're going to talk about 5 things. We will not get to all 5 of them today. We'll probably get to maybe just one of them. I'm not even sure if we'll get beyond one. But what we're going to talk about is, first of all, what do I mean when I say a column store database? So we're going to talk about row versus column. We're going to talk about a key characteristic of in-memory column store databases, and that is the idea of dictionary encoding. We're going to talk about something called attribute vectors. We will talk a little bit about compression and do some examples of that. And we will talk about some of the mechanics of in-memory storage. So this is going to be the focus of the next few minutes we have here together today, and then probably our time together next week. Examples of this would be SAP HANA, IBM Netezza, not sure I spelled that right, Oracle Exadata, there's a company that I've forgotten, Sybase has a in-memory column store database. Microsoft has this as well, but I don't know what name they have put on this. This is the contemporary approach to next generation databases. And so this is something that for sure, if you go out and work in a contemporary organization doing things related to database, doing data visualization, working on enterprise information systems, you are going to see this most definitely for sure. One example is SAP HANA. And so this graphic here that I'm showing on this slide is one that SAP sometimes uses to describe what it is that SAP HANA is. And so let's like start at the center and work our way out. SAP HANA is a database system, okay? So when you hear HANA, immediately think it's a kind of database, okay? But it is more than a database, in that what I mean by that is when we came up with the idea, when I say we, when computing professionals came up with the idea of a database, databases, we used to have monolithic applications where data was stored, it was manipulated, it was presented to the user all in one system. And then we came up with the idea of a multi-tiered system where you would have a database layer, a database system, and then you would have an application server that interacted with the database. And the rule of thumb used to be the role of the database is to store and retrieve information. And that's a hard enough job. So let's not make the database do any more work than it has to, okay? When you took a database course, for example, you might have been taught how to write very sophisticated queries that would do very fancy joins and might have calculations built into them, and you would do a lot in the query. Well, what would happen a lot of times is you would graduate and get out into a production environment, and they would tell you, don't write your queries that way. Write your queries to fetch the information in as simple a form as you can, so the database doesn't have to do a lot of advanced processing, and then in your program have the advanced logic to process it, because we don't want to overtax the database, because that hurts our performance. And so there used to be this wall of separation. Well, with HANA, what SAP has said is, let's not think that way anymore. And let's make a high performance database that we can push a lot of work into. So we're going to put this on a server that has as many CPU cores on it as possible with contemporary technology. And we'll get into numbers and other things like that as we go along in our discussion, but we for sure won't get to it today. So we want to create a really, really high performance database server that not only will have as many CPUs as we can throw at it, but we want everything to be stored in memory. Which means that get rid of hard drives. Get rid of even potentially flash memory. I don't know how many of you have laptops currently that have SSD drives in them. That's what I have in my Surface Pro. There's no hard drive in here. And why have we tended now to move away from hard drives recently? It's because hard drives tend to be slower. And if we can move to a solid state drive, that's a lot faster. Well, what's even faster than a solid state drive is, let's not even have drives at all. Let's put everything in RAM memory. So now we're looking at servers with maybe 64 CPUs and RAM memory that we measure in the terabytes. Okay? So we're going to have a server, 64 processor, and let's say 6 terabytes of RAM memory. And the whole database and everything else is going to be loaded into RAM memory. Now, how in the world are we going to be able to do that? We're going to have to rethink how we store the information. And so this database is going to have to handle traditional relational type things. So we're going to have row store database tables, but we're also going to introduce this idea of a column store database table, which we'll have to explain. And then we're even going to re-engineer the database itself, because as we've talked about even today, someone brought this up, updates and operations like that tend to be very expensive, so we're not doing updates anymore. We're going to create these database tables that are insert only, and we'll talk about how that works here. But basically what SAP and their competitors done is they sat down and said, you know, technology has changed a lot. And one of the things that we have now is the potential to have multi-core CPUs. RAM memory gets cheaper every year. Maybe we can create these really high performance database systems and have that change the way we work. And when we say change the way we work, that means that we can do real-time analytics, which you see here at the top, and real-time transaction processing all in one system. So now we're going to have one very, very high performance database that we're going to use for our transactions and our analytics. And because we're putting everything into this high performance system, now we can, what you see here in the outer ring, we can analyze, we can predict, and we can execute in real time in our organization. We can know what literally is going on this very second, because all of that information is going into this system, and we can tie it to analytic applications that operate in real time. See, the problem with this before, and I'll say more about this next time when we get together, with the old school, I'm not going to back up, but, well, let's do this just for the sake of fun. Do you think that anybody back then that used those systems would have ever envisioned an iPad? You know, that would have been the stuff that would have shown up in science fiction, you know, and literally did. Star Trek kind of had those ideas long before anybody else did. But nobody back then, you know, that was handed a stack of green bar was thinking, boy, I can't wait till my iPad comes in. You know, until that technology was invented, nobody had any idea. Well, now, you know, we're here, but now we have stuff like iPads, and we have all of these things that arguably we're not really leveraging. And part of it's because relational databases were invented on the IBM 360. Okay, that's where Oracle used the IBM 360 to create the idea of a relational database. But queries back then didn't exactly operate lightning fast. You know, those were slow systems. So you might write a query and have to wait 5 or 10 minutes for the result to come back. Well, would you ever want to like run an application on your iPad where when you said, okay, run this app, you had to wait 10 minutes for it to load, and then anytime you asked it for a question, you had to wait 20 minutes for an answer? Nobody would find that acceptable today. We couldn't deliver. You know, if you had a time machine and could take this back to 1970, do you realize how useless this would be? I don't know if you ever thought about that before, but if you took this back to 1970, there's no Wi-Fi, there's no internet, there's no cell phone. This would be just a, you know, once the battery ran out, particularly, this would be worthless. I mean, you couldn't do anything with it because this is part of a whole system of technologies that make this work. Well, even here, a lot of the stuff that we're doing isn't high power enough and performance oriented enough for us to make an app out of it. But with what we have now in these high performance systems, we have a lot of really interesting new opportunities. So you can see I've got 2 videos that I want us to watch, and this